reminders of stuff. On the course web page, and on Canvas too it should be. There are posted links to YouTube videos which just talk through each of the benchmarks from this most recent round of benchmarks. And those recorded videos are more than just like writing the proof. If you just want to see that, click on the link that says solutions, it'll take you to a PDF. These recordings include how to come up with the proof, so like the scratch work that I wouldn't want to see on your final write-up anyway, and then turning that into the actual proof. Some interesting things happened. People had interesting and correct and novel ideas on the monotone convergence problem, so that one got a little bit longer because I wanted to write up two different arguments, one of which doesn't use monotone convergence. All right, so let's remind ourselves where we stopped last time. So we stopped last time by introducing the notion of compactness. And we showed that every compact set is closed and also is bounded. The goal today is the Heine-Borel theorem, which says that that's actually an if and only if. Which is useful because compactness is a reasonably explicit thing to talk about. No, closedness is a reasonably explicit thing to talk about. Boundedness is totally explicit, you just need bounds. Compactness is a really powerful thing. It lets you turn like an infinite collection of conditions down to a finite one, which you can use to do lots of stuff. We're going to prove that converse. But before we do that, let's put definitions up. What does it mean to be closed? A set C is closed if all of the limit points of C are in C. If C contains all of its limit points, and let's maybe in order to make sense of that, let's also remember what a limit point is. What does it mean to say a point P is a limit point of a set C? Flip to the previous page if you got it.
I think it's something like for no greater than 0, or was it no?
What letter do you want?
I guess it doesn't matter what letter.
So just pick one.
For epsilon greater than 0, I think it's P minus epsilon, and P plus epsilon is then C.
With that?
Yeah.
Not like. And notice that would say something like really strong. So you said that for every epsilon bigger than 0. If epsilon is like 10 trillion, that would mean P minus 10 trillion to P plus 10 trillion has to be a subset of C. That seems like not right, right? That shouldn't be what limit points mean. What's the informal thing that a limit point should mean? Say louder. Just say that again.
The limit of the set?
Yeah, it's like a limit of points in the set. So let's think about what that one limit means. That limit should mean points in the set get really close to this point P. Okay, so that means for every positive number epsilon, there should be stuff that close to P that's also in C. So let's try to revise this.
So this is P
minus epsilon plus P plus epsilon in C. That is not P.
Yeah. So there exists some x in P minus epsilon to P plus epsilon such that x is in C and it shouldn't be equal to P. You could say this in the language you were saying before as P minus epsilon to P plus epsilon intersect C minus P is not empty. Cool. We feeling pretty good? All right. Bounded. What does it mean for a set to be bounded? Has an upper and lower bound. It has an upper and a lower bound. And we know what upper and lower bound means, so I won't bother writing those. C is compact. What does that mean?
For every open cover capital operates as a finite subcover.
And there's one other notion that I'll just need in the proof, and that's the notion of a supremum. If I say S is the supremum of a set big X, what does that mean? There are a handful of different correct answers here.
For every little x, big X, little x less than or equal to S.
That's half of it. That's what it means to be an upper bound. You need a little bit more.
What's the least upper bound?
And that's like somehow good enough. Every other upper bound is at least as big as S. And let's rephrase that a little bit. If Q is less than S, then Q is not an upper bound. Which is the exact same statement again, just the contrapositive, I guess. Those are some ideas that'll be relevant. Let's now focus on the proof. So I'm going to leave those on the board because we'll point to those a few times. So the Heine-Borel theorem says let C be a subset of R. C is compact if and only if C is closed and bounded. And let's see, that's an if and only if claim, so I need to prove both ways. So one of the steps would be assume compact, show that it's closed, show that it's bounded. But in fact, last time we've already shown that that compact implies closed and compact implies bounded, and I've given a space there to write the proposition that points to those. Which proposition says compact implies closed? Five 5.2.8. If compact, then closed. Bounded? Well, maybe I'll start with this much. It's probably section 5.2. Yeah, that sounds right. Compact implies bounded. So to do each of those, we picked an open cover, used that we knew it had a finite subcover, and then used that finite subcover to make a conclusion. This time we can't do that. In order to show something is compact, you have to start with absolutely every open cover. You don't get to know anything about that open cover. It could be as wild as you want. And now you need to show that that open cover has a finite subcover. So, if we want to prove it this way, we have to assume that C is closed and bounded. We want to show C as compact. So if we want to show C as compact, definition of compactness is on the board. So what is it that we need to show if we want to show that C is compact? Like, I know it's literally just like written on the board, but like,
For every open cover, there's a finite subcover.
all right. And that statement, at least, I misspelled the word every, so I stuck that Y in at the end. I shouldn't use the non-always again. I won't anymore. Every open cover is a finite subcover. That's what we need to prove. That looks like a universally quantified statement. So we better start by considering any such thing. Let's let MathCal F be an open cover of C. And I know the definition of open cover isn't written on the board yet. And I don't think it will be. An open cover is a collection of open sets. So MathCal F is a bunch of open sets. And if you union up all of those open sets, you contain X. Every element of X is in one of those open sets. We need to show that we can get away with only finitely many. And here's how we'll do it. I'm going to introduce a new dummy set, big X, which is only going to be local to this proof. And here's the definition of the set big X. I will set big X to be the set of real numbers R, which satisfy that if you take C and you intersect it with negative infinity to X, that is covered by a finite subset of MathCal F. So maybe a picture is in order. So here is a picture of a closed bounded set. In fact, it's a closed bounded interval. In order to show that this set admits a, well, here's what it means to be in the set big X. It would mean that if I take all of this intersect C has a finite subcover. And so that's just like a smaller compact set now. That seems fair enough. So I'm going to let this X run over all the real numbers little x. And I'll say that this real number is in the set big X if that intersection has a finite subcover. That seems sensible? Does the definition at least make sense? So here's what I'm going to do. I'm going to study that set big X. And here's what I'll try to do. So if I knew that like a number over here were in the set big X, that would make me really happy, right? Because I need to show that that red interval has a finite cover. Well, if I can cover everything in that interval up to this point, well, that's just everything in the interval. So if I can show there's stuff in the set big X that's bigger than an upper bound on C, then I win. So in fact, here's the strategy I'll try to show. I'll try to show X is not bounded above. That'll be too hard to do like all at once. So let's just start with this. Let's try to show that X is not empty. So, I don't know, I'm even going to label those endpoints. I don't know, -3 to 5. So if that's -3 and that's 5, can you come up with something where it'll be like pretty easy to show that this set big X, or that this, can you find me an element that'll be easy to show as in the set big X? try -3. So, in order for -3 to be in that set, I'll need C intersect interval from -infinity to -3 has a finite subcouple. What is that intersection? For this particular example that I've drawn.
Just -3.
Just -3? Ooh, that's handy. Singletons are compact. They're like obviously compact. There's an element of MathCal F that contains 3 because 3 is in the set big C. Just take that element. In fact, I think we could have done easier. How about if we take -4 instead? Because then what's the intersection? Empty set? Oh, it's easy to come to the empty set. You don't need to use anything. So, step 1, and in fact we have the idea now. Big X is not empty. And here's how we'll do it. What was important about this -3 in this like very explicit example? Why did you use -3? Yeah, there'd only be one thing. There's nothing in the set that's less than 3 was the helpful thing. It was a lower bound. So, let's use that. C is bounded below. Let's let L be a lower bound. And we could then just show that L is in the set, but I want to be lazier than that. I'll use L minus 1. Let's show that L minus 1 is in C. The first thing to notice is that C intersect that interval is the empty set, and there's space on the next page. So, let's put the details here. So, given L is a lower bound on C, show C intersect -infinity to L minus 1 is the empty set. That looks like something that you could prove. And showing something is the empty set is like a very negative statement. So maybe it'd be easier, like, because what does it mean to be the empty set? It means that nothing is in there. So let's proceed by contradiction. Let's suppose something more in there and get a contradiction. Think you can get that? Yeah, so come up with that contradiction real quick. Cool. Convince me of that. So, how did your contradiction proof go?
So if X is in the intersection, then X is less than or equal to L minus 1.
Mm-hmm.
And then, but because it's in C, it's greater than or equal to L.
That sounds like a contradiction. And maybe I'll put something before that if. If not, then there is some X in that intersection. Cool. We feeling pretty good? I guess your starting point's just fine, because then the contradiction would be, well, that means there's nothing in the intersection, so it's empty. All right. So, in particular, then, I claim that the empty set is a finite subset of math cal F, which covers C intersect negative infinity to L minus 1. So I guess there are two things, well, let's check off three things, because this is what we'll need. Is the empty set a subset of math cal F? Is every element of the empty set an element of math cal F? Yeah, there's nothing to check. There are no elements in the empty set. 2, is every element, well, does the empty set have only finitely many elements? Yes, it has 0 elements. That's fine. Does it cover this intersection? What would that mean? That would mean everything in that intersection is in an element of the empty set. Are there any elements in that intersection? Nope. So none of them are in an element of the empty set. There's nothing to check. It's all vectors. Cool. So, does that mean that the set big X is not empty? What element do we have in there? Maybe I'll put the definition of big X on the board too, because we'll refer back to it a lot. Big X is the set of all X in the real number line such that C intersect negative infinity to X as a finite couple in. Don't know if that's verbatim, but that's close enough. So what element have we produced where we have a finite couple? L minus 1. We showed that the empty set is such a finite couple. All right, and now I don't care what element that I found in the set big X. L would have been the more obvious choice, but it would have been just slightly harder to show that it has an open couple. Because then you would have had to show that a single element is coupled instead of no elements. Bounded above. So next goal, show that big X is not bounded above. That's what I want to prove. Let's proceed by contradiction. If I want to show that this set big X is not bounded above by contradiction, then what do I assume? That it is bounded above. All right, so what do I have right now? X is not empty. X is bounded above. What's special about non-empty sets that are bounded above? They have a least upper bound. And if you like the Latin, use supreme. If you don't like the Latin, use least upper bound. Let's let S be the supreme of X. And remember, I want a contradiction. I want to get something to go wrong. So I guess that means that sup of X, I'll either want to show that it's not actually the least upper bound, there's a lesser upper bound. Or I'll want to show that it's not an upper bound at all. And I think there are two cases that will follow. This element, little s, it's either in C or it's not in C. It might not be obvious why those are two good cases to use, but those definitely are two cases that cover all of reality. So, let's do it. There are two cases. Either S is in C or it is not in C. Let's suppose that S equal to the supremum of X is in C. let's just follow our nose and see what we can do. That little s is in the set big C. Math Cal F is a cover of all of C. So if Math Cal F covers all of big C, then it's got to cover S at some point. Oh, cool. So there's something in Math Cal F so that S is in that something. Oh, let's write it down. And I picked a variable name, I think. So there's something in Math Cal F which satisfies that S is an element of V. So there's like a weirdness there, right? We have S is an element of V is an element of Math Cal F. S is a number, V is an open set, so it makes sense to ask if S is an element there. It's the right flavor of thing to be in V. V is an open set. F is a collection of open sets, so it makes sense to ask if V is an element of that open set. And there's something later on where I make exactly that type of screw up later on down the road. All right. V is open. Oh, I didn't have us write down the definition of what it means to be open. What does it mean to be open? Nope, that's closed.
All points A and B are interior to E.
So S is in V, so S must be interior. Let's also remember what interior means. What's that mean? Flip back if you gotta. And this is something that, like, if you're ever reading like a hard math paper, is something that you just have to do. Right? They'll make definitions earlier in the paper, and then they'll just reference those definitions later on. If you want to really understand what's going on, you kind of have to have multiple pages open a lot of times. So anyway, interior, what's it mean?
There's some delta greater than 0 such that U minus delta, the point U minus delta, U plus delta
I used S instead, just because S is the variable I care about right now. Cool. Let's use that. So this point S is interior. So that means that there is some epsilon bigger than 0. I'll use epsilon instead of delta just because that's what's in the notes right now. So that S minus epsilon, S plus epsilon is a subset of V. So the picture here is going off, I bet. There's the point S. There's S minus epsilon. There's S plus epsilon. So this whole red thing is a subset of V. We feel pretty okay? So let's use that it's the supremum. S minus epsilon is less than the supremum. The supremum is the least upper bound of X. So S minus epsilon is not on upper bound on the set, big X. So there must be something in the set big X that's bigger than S minus epsilon. So there's this X, so that S minus epsilon is less than X. I feel pretty okay? So here's the game we're going to play now. That thing I just indicated in blue is in the set big X. So at least up to that blue point, I could find a finite cover. All right, that's good. Oh, but this UN thing is a subset of V, so let's add V to that finite collection. If I add a single element to a finite collection of things, is that still a finite collection of things? Ooh, that means I can by taking a slightly bigger finite cover, I can cover more than I used to. In fact, it looks like I can cover all the way to that. And I could go farther, but I have to stop at some point, and that's good enough. So it sure looks like this thing will also be in X, because I can take the old finite cover and stick V in there too. Why would it be a contradiction if that point were also in X? Yeah, S wouldn't be an upper bound, but it's in supremum. So the supremum isn't actually an upper bound. That's a contradiction. So let's try to play that game then. So this little x is in big X. So the definition of big X says that because that little x is in big X, C intersect negative infinity to X has a finite cover. So let's give it a name. As little x is in big X, the definition of big X implies that there exists some finite subset, mathcal G sub X, such that mathcal G sub X covers C intersect negative infinity to X. And just like the reasoning we just used, the logic that I want to use is let's just add the open set V in there. That will now cover C. And it'll cover more than it used to. And let's just convince ourselves of that. So remember what it means to be a cover. It means everything in this set has to be in something in there. So to do that, so we need to show that for all, P in C intersect negative infinity to S plus epsilon over 2, there exists a U in G sub X such that P is in U. So let's try to do that. So let's let P be in C intersect negative infinity to S plus epsilon over 2. And I think there are two cases to think about. If P is bigger than or equal to X, then, well, let's see. There's X. I guess that blue line looks like the midpoint. So the point P is in there. So I think I won't justify what I'm about to write, but tell me, if P is something in that range, what's an element of this collection that contains it? Big V? Then, let's see, P is definitely in S minus epsilon to S plus epsilon, which is a subset of big V. So, P is in big V, which is an element of GX union singleton V. Cool. On the other hand, if P is less than X, then I guess I need to convince myself that P has to be in one of these GXs. Be in an element of GX. So let's try to do that. Well then, that means that P is in, it's still in C, right? It's in C intersect negative infinity to X. Does that follow? Do we know that P is in C? Do we know that P is less than or equal to X? Yeah, in fact, it's strictly less than X right now, but that's even better. So, as GX covers, P is in some element of GX, which is a subset of GX union singleton V. So that was all like, the statement was super intuitive, and then like the actual argument you follow your nose and have to do like a set. Questions right now? All right, so I think I'm ready to get a contradiction. So, explain to me why that means that S plus epsilon over 2 is in the set big S. There's the set big X. So if S plus epsilon over 2 is supposed to be in this set, I need this thing to be true. Does C intersect negative infinity to S plus epsilon over 2 have a finite cover? What finite cover is it?
G, or Mathcal G, so that is union.
Yeah. So G union singleton V is a finite cover of C intersect negative infinity to S plus epsilon over 2. So S plus epsilon over 2 is in X by the definition of big X. Explain why that is a contradiction.
Well, that's S plus epsilon over 2 is greater than X. So it would be an intersection of C and negative infinity to X.
So I think here's the more important part. It's bigger than big S. Because what was special about no, not big S, little s. These s's are just elements, they're not sets. S plus epsilon 2 is bigger than big S, and what was special about big S? So something bigger can't be in the set. There's the contradiction. Let's make this go away. Groovy. So, what was the assumption we made? We assumed that S was in C and got a contradiction. So that must mean that S is not in C. So, let's get a contradiction in that case. Step 2b. What will we show here? If S is not in C, we will again show that S is not an upper bound. So, here's the logic we'll use this time. Since S is not in C, and C is closed, then that's wrong. C is not a limit point if C is nonsense. C is a set. points can be limit points of sets. So if S is not in C and C is closed, then what can you conclude is not a limit point? How about S? C contains all its limit points, so if S were a limit point, it would have to be in C. So S cannot be a limit point of the set big C. Let's negate the definition of a limit point and see what we get. So, since S is not a limit point of big C, I can negate that. So instead of for all epsilon, we will see that there exists an epsilon bigger than 0, such that the interval from S minus epsilon to S plus epsilon intersect C, but then take away S, is empty. All right. So what does that say? That says that the only thing in S minus epsilon to S plus epsilon that might be in C is S itself. But is S in C? Nah. As S is not in C, in fact, S minus epsilon to S plus epsilon intersects C equals the empty set. So let's draw a picture again. There's this point S. There's S minus epsilon. There's S plus epsilon. There's nothing in C in that interval. So now we use the same sort of idea. I can find something in X that's like there, right? So that means I can cover everything in the set big C that comes before that point. Ooh, but everything in C that comes before that point is the same thing as everything in C that comes before that point, because there's nothing in C in between them. That feel pretty good? So we'll get like the same sort of contradiction. So I'm going to write down the argument. It'll feel super similar to what we just did. So as before, since S minus epsilon is not an upper bound on big X, there's some little x in big X with S minus epsilon less than X. The definition of X now lets you conclude that this happens. So we get to conclude that there is some finite collection Gx, a subset of F, which covers C intersect negative infinity to X. Plugging along okay? All right. I claim that it also covers everything up to S plus epsilon over 2. So let's do that. So let's consider any P in C intersect negative infinity to S plus epsilon over 2. So there's S plus epsilon over 2 as S minus epsilon to S plus epsilon intersect C is empty, it must be that P is less than or equal to epsilon. Do you buy that? Right, otherwise P would be bigger than epsilon, so it would be between, oh no, not bigger than epsilon. S minus epsilon, right? Right, if P were bigger than S minus epsilon, then it'd be bigger than S minus epsilon, but less than S plus epsilon over 2, so less than S plus epsilon. So it'd be in the interval, but it's also in C. Oh, but that intersection is empty. All right, cool. So, P is in C intersect negative infinity to S plus epsilon over 2. Is it clearer why that follows? Is it in C? Yep. Because it's in an intersection of C with some stuff. Do I know that P is less than or equal to S plus epsilon over 2? Oh, that should be a minus. Oh, that should be a minus. Right, it's less than S minus epsilon. So yeah, it's less than S minus epsilon over 2. Ah. Oh no, that's not what I want. There's what I want. Right, there's X. I in fact know that P has to come before S minus epsilon. X is bigger than that. And what's the point of that? So, as G X covers, P is in some U that's an element of Gx. And let's see. So why do we get a contradiction now? Well, let's make the same argument. That means S plus epsilon over 2 is in big X, because we've shown that this intersection has a finite coupling. The thing that we call Gx is that finite coupling. But that thing's bigger than the supremum. All right, so the proof is actually going to flow really fast now. So what do I now know? I know that X cannot have a supremum, so it is not bounded above. But C is bounded above by assumption. So let's let U be an upper bound on C. Let's ask this question. Is it possible that U might be an upper bound on big X? Nope. Why? Yeah, it's got no upper bound, so this can't be one. No. So, since U is not an upper bound on X, there has to be some little x in big X with X bigger than U. So by the definition of X, there is some finite Gx contained in F that covers, C intersect negative infinity to X. But I claim that C is equal to the C intersect that thing. And that actually seems pretty obvious, right? I guess if you want to do a full-blown set containment proof, that containment is automatic. Intersection only makes things smaller. So let's let little c be in big C, then C is less than or equal to U, since U is an upper bound, is less than X. So C is in negative infinity to X. Hence, C is in C intersect negative infinity to X. This means GX is the needed finite subcover. So, I think here's the takeaway. This was a proof with a lot of moving parts, right? It was definitely the type of proof that's like beyond what I would expect to be like come up with a bowl as like a homework problem. There's a lot of stuff in here. So I think I want to say like what are the takeaways here? Right, this is another example where like including this notation where you have something that depends on some variable and you just encode that in the notation is useful. That let us talk about different gx's for different x's. But the useful thing here is as soon as a set is closed and bounded, that set is compact. So you know what, I say here to use the definition, but take your pick. Is the empty set obviously closed? I guess you have to show it has no limit points, because it can't contain any limit points. Is it bounded? The empty set? Everything in the empty set is less than 5. There's nothing in the empty set. Everything in the empty set is also less than 16, because there's nothing in the empty set. So yeah, closed and bounded. Singletons are compact. So prove these things by now appealing to Bolzano-Weier's stress. Cool. I passed time. Yeah.
To the other page. Could you flip to the
Oh, yeah. The page we were just on? All right. And the thing will crash as soon as I hit stop record, so